Hello and welcome to trigonometry class. Hey, we're going to start learning vectors today. This is the first week after our cool coronavirus, vacation, I guess, staycation. So here we go. Vectors are line segments that have direction and magnitude. You may have remembered our friend Vector from Despicable Me. Alright, a directed line segment just means that our line has some sort of direction and it's a segment, so it does not go on forever. So in this case, this one is vector AB. You'll notice that this looks exactly like a ray, except you're missing that little part of the arrow right there. That's the difference between a vector and a ray. Also, rays, remember, went on forever in one direction, whereas a vector starts at one point, ends at another point. But this thing is there to tell us that there is a direction to it. It goes from A to B. Another way to write the name of a vector is a lowercase bold letter. That's how you know that something's a vector. Magnitude is the same thing as distance. So you'll use the distance formula later on to find the magnitude of different vectors. The little absolute value bars that look like they're doubled on both sides, that tells you the magnitude. So that's the distance from point A to point B of this vector. When you hear me say initial and terminal, we remember that from the very beginning of trigonometry in January. Initial means beginning, terminal means the ending. A vector is considered to be in standard position when the initial point is on the origin. So if you're starting at 0, 0, you're in standard position. By the way, the direction of this vector might be slightly different in your notes. If it is different, please change it so that we're not confused. Okay, now that you've changed it, here's how you find component form. You're just going to take, here's our cool formula right here, you're just going to take, first, start where the arrow is pointing. So in this case, the arrow is pointing at point Q. So I'm going to start with the x value of point Q, and I'm going to subtract the other x value from it. So there's Q1 minus P1. Then I'll do the same thing with the y values. Take wherever my arrow is pointing, start there, take that y value, subtract off the other y value. There it is here. That will give you something that's in component form. Here again, like I promised before, these things, remember, mean magnitude or the distance, and this is the distance formula. Again, this is going to be so simple once you do an example. The cool thing about the distance formula is if you put it in component form, all you're doing is you're adding the two numbers in component form after you've squared them, and then you square root it. Again, let's do one together, and that way I will prove to you that it is super easy. Alright, this point where we're starting, this is the point -3, 2. How did he do that? Well, he just went left 3 and up 2. This point is the point 1, -4, so I'm going to write 1, -4 right here. Alright, now I'm going to make these things, I call them elbows. So make the little elbow brackets. And then remember, just like I said before, we're going to start wherever the arrow is pointing. The arrow is pointing here at this point, so I'm going to start at that point. Take my x there and subtract off the other x here. So it's going to be 1 minus, this is -3. You know I don't like negatives touching each other, so I put a plus there. Then over here, I'm going to start with wherever the arrow is. It's -4 minus the other y value, which was 2. So the component form of this vector is 1 plus 3, which is 4, comma, -4 minus 2, which is -6. -4, or +4, -6. Now, something amazing about this, let me take this dot right here and draw a really straight line all the way down to that arrow. Now, if I took this vector and I moved it so it started at 0, 0, look at where it ends up. 1, 2, 3, 4 to the right. 1, 2, 3, 4, 5, 6 down. Not a coincidence. That should happen. So component form, remember, starts at 0, 0 and works its way over to wherever it's supposed to end. Notice that these lines are parallel to each other. In fact, they're going to be called equal vectors. Even though they're not in the exact same spot, it doesn't make any difference. They're considered equal vectors because the magnitude or the distance is the same, and they're going at the same angle and the same direction. Alright, let's talk about 3D graphing. 3D is much more useful than 2D because if you get into any cool graphic designs or anything with cameras that are online, such as you could use Photoshop to do this, or Premiere Pro, or any of the Adobe Suite things, especially with videos where you have an up and down and there's depth to your problems, to your video that you're doing, you're going to find the magnitude of this 3D vector. So first, let's start off by figuring out what the 3D vector is. Now, we're used to just having an x and a y, and that's all. However, this has an x, a y, and a z. So you're going to think of this little gray rectangle here as being your piece of paper. Your piece of paper is going to be flat on your desk. The x is going to go just like normal to the right. The y is going to go up and down on your paper that's flat on your desk. Alright, now after that we're adding a third component. This one is coming off of your paper and going up into the air. This is the z vector. This is the z axis and the z direction. So z is going to come off of your paper. Freaky. Alright. Let's start with the x. We're going to go to this point right here. So if you noticed, I drew the little up and down and across lines to help you out. So the x, I went across 3. So I'm going to put 3. I went up here 2. And then I went straight up into the air off of the paper, and I went up to a height of 5. So that vector right there, from the origin all the way up off the paper in the air, hovering in the air, there's this point, and we drew a vector from 0, 0 on your paper up in the air to that point. To find the magnitude, we are going to just do this, and we're going to find the magnitude just like we were supposed to find the magnitude of this problem here, but Mr. Robertson's not so good at reading directions sometimes. So let's go back and do this magnitude. So we found the component form, but I realized just now I didn't do the magnitude. So here's all you're doing. You're going to take whatever the x part is and square it, and then add to that whatever the y component of that was. Square them, add them, and then square root the answer. So on your calculator or in your brain, you're doing 4 squared, which is 16, plus 6 squared, which is 36, to get 52. We know that 52 is the same thing as 4 times 13. And we can reduce this because the square root of 4 is 2, and the square root of 13, we don't know the exact value, so we're going to stick with that. So if I asked you for the exact value of the magnitude, that would be 2 square root of 13. If I asked you to reduce, or not to reduce that, to put it in decimal form, you could just type 2 square root 13 on your calculator, and that should give you 7.211. To make extra sure that you actually did this reducing correctly, it is super easy to tell. All you have to do is go back to that original square root that you started with, the square root of 52, and type that into your calculator. That should give you the exact same decimal value as when you reduced it. So that indeed is 7.211, and so is that, so I know that I reduced this correctly. So my magnitude, or the distance of this vector from start to finish, is about 7.211. Now, back to our 3D graphing. I'm going to do the exact same thing where I'm squaring and adding the x, y, and also the z components of this three-dimensional vector. So I put in my 3, my 2, and my 5. So this gives me 3 squared plus 2 squared plus 5 squared, which is going to be 18. That's not 19. That's as far as we can reduce it. If I asked you to put it in decimal form, we would type square root of 38, which would give us about 6.164. And so that's the distance from here up to there. Does the answer make sense? Yes, it does. If I went straight up, it would be 5. So if I went and stretched it out kind of diagonally, it's going to be bigger than 5. 6 makes sense. Now let's talk about zero vectors. Zero vectors are super easy. The magnitude is 0, so that's just a point. Equal vectors, like I talked about before, equal vectors are like these two. They're not necessarily in the same place, but they do have the exact same direction. These are going down and left, and they're at the same angle, they have the same slope. They're parallel, they're not going to touch. So they again do not have to be in the exact same place to be considered equal vectors. We're going to show that these two vectors, the red and the blue, are indeed equal vectors. First, let's start with, which one is this first? So it looks like U is going to be the blue one. So let's start with U. And let's put it in component form. So the terminal point is 4 for the x value. The initial one for the x value was 0. Terminal y was 2. Initial y was 0. So I do 4 minus 0, 2 minus 0, and that's it. So that is U in component form. Now let's do V in component form. We're going to do the same thing. We're going to start with the terminal point, subtract off the initial. So this gives us in component form 4, 2. Yes, indeed, they're the exact same. All you have to do is show that two component forms are the same, and that tells you that those two are equal vectors. Now let's move on to vector addition. Vector addition is really, really simple. If you have two vectors, like let's say 1, 2, and 3, 4, and you have them in component form, all you're doing is you're just adding the x values. So in this case, that would be 4. And you're adding the y values. 2 plus 4 is 6. And that's it. Now, if we're talking about it graphically, what you're going to do is you're going to take U plus V. There's my V. And in order to do U plus V, I'm going to basically just magically drag V to the very end of U so that U is pointing to the beginning of V. Got that? So then my final answer will be from the start of U all the way up here to the end of V. So this little teal vector is U plus V, just like that. This is called the parallelogram law because all you do is you move the second vector up to the end of the first, and it would create a parallelogram if you do it perfectly. Your final vector, your answer, is from the start of U to the end of V again. Scalar multiplication. So with scalar, that means you're just taking some number and you're scaling the vector, scaling it, making it either bigger or smaller. It will still go the exact same direction, but this time it's going to be longer or shorter. If you have a scalar that's negative, it's going to go the opposite direction. So all you're going to do is, like if I were making a negative U, I would take this arrow that was here and I would move it to the other side. I would flop the arrow to the other end if it's a negative U. Negative V, the same thing. My arrow's here right now for regular V, so for negative V, I would just flop my arrow to the other end. This will make sense once we do it. Scalars, again, will change the magnitude or how long a vector is, but it's never going to change the slope or the angle. Let's do some vector operations. Here's V and W both given to you, and the math people want to know what's 2V minus W. So I'm going to take 2, put a blank, minus, and put a blank. Inside those blanks, I'm going to put whatever V is where the V was, and W is 2, 5, so I'm going to put a 2, 5 here. Next, 2 is our scalar. So what I'm basically doing is I'm taking the vector negative 3, 4, and I'm doubling it in size because it's being multiplied by 2. So what you can do is just multiply, distribute the 2. This becomes the vector -6, 8. And then I'm going to copy this part down. So now I'm going to go ahead and subtract my x values. So -6 minus 2 gives me -8. And 8 minus 5 gives me 3. So 2v minus w is -8, comma 3. That's it. Now let's do the same thing, but let's do it graphically. So here was the point -3, 4. There was the point 2, 5. So to create the vectors, I started in standard position, which is 0, 0, up to -3, 4. 0, 0, up to 2, 5. Now you've noticed that my arrow's in the wrong spot. Normally it should be here. However, since this formula has a minus w on it, I'm going to go the other direction instead. So I flopped the arrow to the other side to create minus w here. Alright, so since this says 2v, I'm going to take v, I'm going to double it in size. Now the easiest way to do this on your graph is just to do some counting. So if I go up 1, 2, 3, 4, and left 1, 2, 3, if I went up another 1, 2, 3, 4, and left another 1, 2, 3, that would take me to here. So this long vector, keep going, there we go. That long vector is vector 2v. Okay with that? Good. Alright, now the minus w, look, I already did it. I just changed the arrow so it was going to the other place. But remember, in order to do vector addition or subtraction, I have to take this vector and move it to the end of the other vector. Again, we're just going to count kind of like the slope of this in order to figure out where to go. So from start to terminal, we're going down 1, 2, 3, 4, 5, left 1, 2. So I go up here, down 1, 2, 3, 4, 5, left 1, 2, put my dot there, draw my arrow. These should look like they're parallel because they are. Minus w, remember they're equal vectors, they both go in the same direction, same angle, same magnitude, they're the exact same vector. Now, I'm not finished with my final answer yet. For my final answer, it is this vector right here from the initial point, 0, 0, all the way to where I just finished. So this purple one is 2v minus w. Let's see what that point is. The point is -1, 2, 3, 4, 5, 6, 7, and 8. So -8, and then up 1, 2, 3. -8, 3. Hey, if you remember correctly, that was our answer here. Coincidence? No, it was not. It worked out perfectly. Now let's talk about unit vectors. Unit vectors are important because they have a distance of, you guessed it, 1 unit. Remember the unit circle, how its radius had a distance of 1 unit? Well, this is the same deal. This is going to be a vector that has, again, a length of 1 unit. This will be helpful when we start doing trigonometry again in just a few moments. In order to find the unit vector, I like this formula right here. Now it's not going to make much sense to you yet, but you're going to take 1 divided by the magnitude, and then you're going to multiply by the original vector that you started with. U again is the unit vector. That's why we started with a U. So in this case, we're going to find a unit vector with a direction of -1, 2. Then we're going to prove that it really is a unit vector and find its magnitude, and if we did it correctly, the magnitude should be 1. Alright, so let's go. First, I need to find the magnitude. So first thing I do is do my little double bars of the V. In order to do the magnitude, that's the distance, remember, I'm going to do the distance formula. Since it's in component form, it is super easy to do. I take the x value and the y value, I square them, I add them together, And my calculator says that that is 5. So my magnitude of the original vector is the square root of 5. Now, in order to find the unit vector, I'm going to put a u there. That's going to be 1 divided by that magnitude, square root of 5. So that 1 is always there. The fraction bar is always there. This thing, the little elbows, these will always be here, and you're just going to take whatever your original vector was and copy it. So that part's easy. The only hard part is doing the distance formula and putting it there, and that's not even that hard. Finally, we're going to distribute our scalar. This scalar is going to make this vector smaller so it has only 1 unit in length. I'm going to multiply 1 over the square root of 5 times each of these. If it helps you to think of it correctly, we're going to put both of those over 1. So now I have a unit vector of -1 over square root of 5, comma, 2 over square root of 5. That is my unit vector. Now this question asks me to go ahead and prove it that I know that this is a unit vector. So I can find the magnitude of this unit vector by doing the distance formula. So my distance formula is, take the x component, square it, add that to the square of the y component over here. So here we go. -1 squared is 1, square root of 5 squared is 5, and now I think you just saw why I didn't reduce that square root so that there's not a root on the bottom. 2 squared gives us 4, square root of 5 squared again gives me 5. Look, I have common denominators. I do 1/5 plus 4/5, that gives me 5/5, which is 1. Next, we're going to find the unit vector in 3D. Somehow my little number came off here, but this is 2, 3, 5, because 5 is the height off the paper going straight up into the air. In order to find the unit vector here, we first need to find the magnitude. We'll call this vector v. And if you'll remember correctly, we already found the magnitude. Pause or go back to that section just a few moments ago, you can do that. But we know that this answer is going to be the square root of 38 for the magnitude. So I'm just going to write that here because we already did that work. Okay, now I'm going to take 1 divided by the magnitude times my original vector, which was 3, 2, 5. My magnitude, we said, was the square root of 38. So I'm going to distribute this now to all 3 of these components of the vector. So I have 3 over square root of 38, 2 over square root of 38, and 5 over square root of 38. That is my unit vector. Unfortunately for us, this didn't tell us that we had to prove it, but if you want to, you could go ahead and find the magnitude of that just in the same way as we found the magnitude of 325 equaling the square root of 38. More vectors. So, on your paper, make sure that I is 1, 0, j is 0, 1. I is going across from left to right in this case. This is the unit vector I. This is the unit vector j because it's going up 1 unit. In linear combination form, we just use the letters I and j instead of having them here in vector form. This will make sense once we do some problems. Oh, pretend you didn't see that. So we're going to let v be the vector with the initial point 1, 1 and the terminal point 5, 3. We're going to write v as a linear combination of the standard unit vectors. So way back, just minutes ago, we did 5 minus 1, comma 3 minus 1, and we found out that that was the vector for 2. You remember doing that, right? Great. Okay, we're going to do the same thing here. We're going to take this now, and we're going to write it as it's going across by a factor of 4. It's going up and down is j. It's going up and down up, in this case, by a factor of 2. All right. Let's move on. Oh, again, pretend you didn't see that. We're going to let u equal negative 3i plus 6j. V is 3i minus j. This is going to ask us to find 2u minus 4v. All right. 2u minus 4v. Notice instead of u I put a blank, instead of v I put a blank, because I can substitute. Instead of u I can put negative 3i plus 6j, and instead of v I can put 3i minus 1j. You don't need the 1, but I put it there just so I don't make any silly mistakes. Then, just like you would do in algebra, we're going to go ahead and distribute that 2, so that's negative 6i plus 12j. We'll distribute the negative 4, that's negative 12i. Did you know a negative times a negative gives you a positive? Yes, indeed, positive 4j. Next, you can combine like terms. You know how to do that. This gives us negative 18j. And this here would give us 16. I misspelled I. I'm sorry. Negative 18i. I got so excited about doing the j, I wrote j. 12 plus 4 gives us 16j. And that's it. If I had asked you to do this in component form, it would look like that. Now, direction angles. Direction angles, mainly what you're going to use are the things that I put in boxes. Now, this u is a unit vector. It's on, you're not going to believe this, a unit circle. Remember from way back long ago when we first started doing trig, we always talked about the unit circle. And the radius had a magnitude or a distance of 1. In this case, this is a vector with a magnitude of 1. So your points will always be cosine, comma, sine. Remember in class I taught you that this was like colorful snot. C and then S, colorful snot, cosine, sine. So for our vectors, we're going to put the magnitude on the outside, and we're going to multiply it by a vector, which is the cosine of theta, comma, the sine of theta. So this vector is going to make it either bigger or smaller than a unit circle if it's not 1, and then this will give us the correct direction. You're probably a little lost, but you'll be all right once we do some problems. Over here, most importantly for the next problem that I do, tangent is equal to the b value over the a value when it's in component form like this. All right, let's go on to an example. So we're going to find the direction angle of this vector. This one's going to be so easy that we don't even need the calculator for it. Let's think of this as, here I'll write it for you in component form. So if I had to graph this, this would be in quadrant 1 because I'd go across 4 and I'd go up 4. So this vector would look something like that, only straight. Alright, since I'm in quadrant 1, I know that I don't have to worry about any negative values at all. And I know that my angle, my answer, is going to be between 0 and 90 degrees. Now, in order to find the direction angle, we remember that slope is the same thing as tangent. And slope is the y values over the x values. So I took my y's, in this case that 4, put it on top. Took my x's, in this case 4, and put it on bottom. If you can reduce, of course you want to. That gives us 1. Now, if you want to remember the cool tricks that I showed you, where you take out your hand, spread it out so it looks like this. If we're talking about tangent, we remember that 0 is 0, 90 degrees, or pi over 2 is undefined. This is pi over 3, so that's the square root of 3. This is pi over 6, so it's the square root of 3 over 3. And this was 1. So in this case, 1 was here at flipper. You should be pointing toward your middle finger, which is pointing at 1. This is pi over 4. Now I'm going to put the little reference angle thing there. You'll understand why. This is pi over 4, which is the same as 45 degrees. Our next step would be to put this into the correct quadrant, because technically when we find this is only the reference angle. However, since we're in quadrant 1, like we said before, the reference angle and your actual angle are actually the same thing. So I'm just going to stick with 45 degrees. Now let's do an example where we're going to need the calculator. Again, pretend I didn't write that. Alright, with the calculator, I'm going to do my tangent again, and I'm going to take negative 4 over 3. This is going to be the inverse tangent. If that confused you, that's okay. We'll just do it like this instead. Tangent of theta equals negative 4 over 3, because it's the y's over the x's. So on my calculator, I'm going to hit, so I just typed in second tangent, positive 4 over 3. I made sure I was in degrees mode first, and then I got 53.130. If you got a really tiny number, go back, check, make sure you're in degrees mode. Okay, next, I know that this is only my reference angle. I have to put it into the correct quadrant. This is not in the correct quadrant because I see that this is negative. This is in quadrant 1 where everything's positive, so we've got to put it in the right quadrant. So easy to do. 3, negative 4. Well, if you were graphing the point 3, negative 4, you go across 3 and down 4. Your vector looks something like this. So in order to get to that vector, you're going to go to quadrant 4. I remember my formula for quadrant 4 is 360 degrees minus my reference angle. I remember that because in order to get there, I go all the way here, 360 degrees, and then I have to back up whatever that reference angle was. So this angle right here is 53, so I take 360, then go backwards or subtract 53 degrees. And when I do that, I get 306.870 degrees. And that's it. That's my reference, or that's my direction angle. And let's see that that makes sense. So if I went from here all the way to there, that would be 270 degrees. If I went all the way to there, that would be 360. So it's got to be somewhere between 270 and 360, which it is. Alright, next, let's go to the next slide. Now I have an airplane. Now it's going at a rate of 200 miles per hour, so the magnitude of this, let's write a magnitude, is 200. That's my speed, the reference angle, because it's going to the x-axis. But if I want to know the true trig angle, I have to start here at the initial line and go all the way around. And so this would be 30 plus 90 plus 90. In order to come up with a component form, all I'm going to do is I'm going to take that magnitude, 200, and I'm going to multiply it into my vector, my unit vector, which is cosine, comma, sine. My angle was 210. My reference angle was 30, which we're going to use to calculate this if we're doing it by hand. Alright, here we go. Let's talk about the cosine of 210 degrees. That's the same as the cosine of 30 degrees, but this is in quadrant 3, so we know it's going to be negative. The sine of 210, again, sine in quadrant 3 is also negative, so I'm going to put a negative sign there so I don't forget. Cosine of 210 is the same as cosine of 30. Cosine of 30 is square root of 3 over 2. This should be pointer if you're using the hand method. Then the sine of 30 degrees, that's pointer, is 1/2. Next we're just going to distribute that 200 through there. So this is 200 over 2 reduces to 100, and we have a negative there. So that's negative 100 square root of 3. Then we have 200 times 1/2. It's negative, so that's negative 100. And that's it. That's the component form of that. My calculator says 173-ish. So if I go left 173 and down 100, does it look like it would be that point right there? Well, yes, indeed it does. So that answer makes sense. Now let's go on to our next example. But before the next example, I'm going to tell you some secrets. So we talked about bearings at the very beginning of the school, or this semester. So bearings, we're going to talk just about airplane bearings right now. Bearings is going to be the B, trig is going to be the T. Now because your calculator does not know how to fly a plane, we're going to need to tell it how to, we're going to need to convert it basically from bearings into trig form. In order to do this, you can just remember these cool formulas. In quadrant 1, you can take 90 degrees minus the bearing, and that'll give you the trig value. And vice versa with trigs and bearings, they can be interchanged. Quadrants 2, 3, and 4, the formulas for that would be 450 degrees minus the bearings. That will give you the trig value. And it works for all the other quadrants. Alright, now we're going to use this on this problem right here. Alright, this plane is traveling at a speed of 500 miles per hour. That would be the red vector there. At a bearing of 330 degrees, at a fixed altitude, no wind. Suddenly it encounters this vector, this green vector, which is the wind, blowing 70 miles per hour. It was going north 45 degrees east. So that would be that vector. This vector, you notice, is smaller because it's only 70 miles per hour as compared to the red vector, which was 500 miles per hour. All I did was I'm doing vector addition, so I'm taking this wind vector and I'm going to move it up here so it's at the very end of the plane vector in order to add them. Okay, these are not drawn to scale, so hey, I'm doing my best. What I like to do is I like to do magnitude, trig direction, mag cosine, and mag sine. Now I've got a problem. First, I need to convert these into the trig values, so pretend you didn't see that. In order to convert it into the trig values, I have to use those cool formulas that I just saw right there. So let's go ahead and do that. The first one was 330 degrees, which in bearings, remember starts here and works its way around. That is definitely in quadrant 2. So I'm going to take 450 degrees minus the 330. So in trig land, that would give me 120 degrees. These are trig degrees, and this is for my plane. Now for my wind was north 45 degrees east. As you can see, that's in quadrant 1. Since it's in quadrant 1, I'm going to do 90 minus that angle, which was 45 degrees. The only way you're going to get the same answer is if you're at north 45 degrees east. Otherwise, all the answers will be different from the original. That was just a coincidence. Alright, and that again is the trig angle for wind. Alright, now that I have those, now you will never have anything here or here. These are just blanks. But what I'm going to do is I'm going to take that 500, the magnitude, times the cosine and the sine of 120 degrees for the plane, and also the 70 for the wind's magnitude times the cosine and the sine of the wind's angle. And I'm going to add them together to get my final answer. Now a lot of people find it really helpful to do this cool chart. So on my calculator, I'm going to do 500 times the cosine of 120. That's what mag cos means, magnitude times the cosine. Now I'm going to take 500 times the sine of 120, that's what mag sine is, and put it in this blank. Same thing here, 70 cosine 45 goes there, 70 sine of 45 goes there. And I did all that on my calculator and got these numbers. Next, like I said before, we're just going to add the x values straight across add the y value straight across. So this gives us the answer negative 200, comma 482. Super easy to check your answer to see that it makes sense. So this red pretty looking vector was the original plane. It's being blown off course this direction. So would negative 200, positive 482 be somewhere in this direction? Oh yes it would. So that looks great to me. Again, we're multiplying 500 cosine 120 to get that, 500 sine 120 to get 433, 70 cosine, 70 sine, and then add your x's across. Those two values give you the plane plus wind vector. Sadly, that's all the time we have for today. I hope you have enjoyed yourself, and if you have any questions, you know where to find me. My email address, in case you don't, is right there at the bottom of my Canvas pages. Also, you know what your assignments are, as they're listed in Canvas as well. I also have my office hours, which are listed on, you guessed it, the Canvas page. Alright, I hope you're doing well. Have a great week. Thanks.